Good morning again. Is it audible right in the back? Okay, great. So gas in galaxies is a very broad topic. We'll focus on two questions. That what role does gas play in galaxies? That's one thing. And second thing is that if we observe gas in galaxies, what is it that we can learn about them? And as I said, this is a very broad topic, but we will take a slice of this investigation which is relevant for square kilometer array, right? So what we are going to discuss today, don't take it as a complete story, but take it as a story which is probably more relevant for the kind of things that we are doing with SK precursors and square kilometer array. We will talk about what we have learned about gas in galaxies and also what is that remains to be learned and how SK can play an important role in coming years. So that's the focus, right? So this is Orion Nebula, the nearest star forming region. We looked at it yesterday also. So, and we are looking at structures which are at parsec or sub-parsec scales here, right? And that's the scale at which star formation is taking place. And star formation takes place from actually molecular gas, dense molecular gas clouds, because that's where the density is high enough that they can collapse under gravity against the thermal pressure or magnetic pressure that may be inside this molecular cloud, right? So what for a galaxy to actually form stars, it has to acquire gas, very low density gas from, let's say, neighboring environment, intergalactic medium, then it comes to interstellar medium, but then there also it may be in the ionized phase initially 10 to the 6 Kelvin, for example. It then cools down, then it may be at the 10 to the 4 Kelvin, may recombine further, become neutral phase, that may be at 100 Kelvin, which may also then continue to cool further if conditions allow. Then it comes down to temperatures of like 10 Kelvin or so, and if it is then in the molecular phase, then it will have be densities which are high enough where it can form stars, right? So that's the long journey which gas has to travel before it can start forming stars. But what happens when stars are formed? Immediately the stars are formed, then they start emitting photons. Photons actually, if they have energy more than 13.6 electron volt, they can ionize hydrogen around it, right? So the same gas from which these stars are formed, these stars start emitting radiation, the gas gets ionized, right? And H2 region is formed, and then this H2 region now will have more pressure, right? Because it's now hotter gas, the gas outside is cooler, so inside is pressure higher, so it starts expanding like a shell. So H2 region is expanding. When stars die, they can also in supernova explosion can inject lot of energy. So when stars form, they will destroy the ambient environment, right? The gas will get ionized and hotter there. So this cycle can continue within galaxies, right? And they can continue to form stars as long as gas is allowed, gas is available and can cool to those high densities and low temperatures, right? So that is the requirement. So in this one picture, everything is happening. Like this, there are many nebula in a galaxy. What we are going to see is that then how we can make sense of observation by observing gas in galaxies, right? That's the goal. But how do we know that there is actually gas in galaxies? Because when we look up, we only see stars, right? Typically, like with our daily experience, if we talk about, if we look at Milky Way, 10 to the 11 stars distributed over a disk of a diameter 10 to the 5 light years, and this is the typical thickness of it. Then if we talk about what is the nearest distance between neighboring stars, on average it is something like few parsec, right? So there is a lot of empty space between stars. Although when we look up, we see that it is full of stars, right? Sky is full of stars, that's how it appears. But when we take like what is the size of a galaxy and number of stars, there is like empty space of few parsec between them. So there is a lot of empty space in galaxies, and around galaxies, of course, like you have been seeing various images since yesterday, like there's a lot of empty space between them as well, right? So the space between stars in a galaxy we refer to as interstellar medium. It's not really empty, we will see that. And like the space which is outside between galaxies is what we call as intergalactic medium. That is also not completely empty. There is even lower density gas present there. We'll focus on what is inside galaxy generally today, right? So interstellar medium. So what does it consist of? It consists of gas. Gas can be molecular, it can be atomic, and it can be ionized, right? All three phases exist in the interstellar medium. In addition, there is also dust that is present in interstellar medium. Then there are also energetic particles, cosmic rays, relativistic electrons, And also radiation field and magnetic fields, right? They also exist in the space that we are talking about. So all these 4 components play a very important role in evolution of galaxy, and we need to consider all of them. We'll of course focus only on the gas phase today. So this medium filling vast regions of empty space between stars and in and around galaxies, that's what we are looking at, is called the interstellar medium. So how did we first learnt about that there is something in interstellar medium and it is not empty, right? So this was again a serendipitous discovery, happened more than 100 years ago. Johannes Hartmann, he was looking at a binary star, again like Orion constellation. Delta Orionis, you can see, is one of the stars that belongs to Orion constellation. It's a binary star. So he was looking at spectral lines which are coming from the atmosphere of this star, right? So since it's a binary star, it is rotating around its center of mass. So the spectral lines will actually slightly move back and forth, right? That's just a simple Doppler motion. So if I observe, then there is an orbital period, and then you will see that these stars, since stars are orbiting, you will see that the spectral lines are moving around. That's what he observed. But he also observed there was a set of lines coming from calcium, which comes at, it's a doublet 3934 angstrom, that's where it is, its rest frame wavelength. That was not actually sharing this motion, right? So that then gives the evidence that it is actually these absorption lines are arising from gas, which is not actually part of the star. So it has to be somewhere in between, right? And what is then in between? That is interstellar medium, right? So this is how we first time learned that, okay, the space between is not empty, it is filled with gas, right? So we are talking about measurement here, right? Not imagination only. So astronomy is all about measurements. And then this is another image like through which we learned that there is actually dust present in the interstellar medium as well, and going from left to right, and then further here if we see what's happening here is that you can see that each panel has a certain wavelength, right? So this image corresponds to that wavelength, and wavelength is actually increasing. And you can see that like if this one image you focus on, you will feel that like, okay, there is nothing here, actually this is empty, right? But as you go further at longer wavelengths, you start seeing the stars emerge, right? So what is happening that this is a cloud which has lot of dust. At shorter wavelengths, light is blocked here, but as we come to longer wavelengths, the light can pass through, right? That's because of this the characteristic size of the dust particles. So as the wavelength gets longer, light can pass around them, and then you can start seeing stars eventually. So this is so what's happening here is that it's showing us that this cloud actually contains a lot of dust. So that's the evidence of like presence of dust in the interstellar medium as well. So whatever we have talked about up to this point is gases, where it all starts as far as stars are concerned, and it also ends there, because when stars die, they expel all the material back into the interstellar medium. Stars from the ISM, but not from any phase of the ISM, although it may contain neutral, ionized and molecular phases. It's the molecular phase that is the important one. And when stars die, they actually enrich ISM through various radiative and mechanical feedback processes. It's not just that they throw the material, but they also throw in a lot of energy back into the interstellar medium as well. And why this kind of feedback is important? Because this kind of feedback can happen from stars, but can also happen from AGN if it is inside a galaxy. And this feedback is important because as the feedbacks come into the gas, this gas can heat up or can get ionized, and as long as it remains hot and ionized, it cannot form stars, right? So some physical processes then have to happen for it to cool down again to be able to form stars. So this feedback cycle or this circular loop that takes place is very it's a very complex one. There are a lot of processes involved, and it's very interesting. And this is what determines the properties and evolution of galaxies. Whether that is a galaxy, whether it will continue to form stars depends on whether it has enough gas, and even after it has enough gas, whether that gas can cool down to temperatures and densities where it can collapse to form stars, right? So that's what determines how galaxies will evolve. But when we look at like ensemble in the sky, this is how it can be classified. This is Hubble's tuning fork. Everyone is familiar with this. On the left side, we have objects which are bulge dominated. They are also gas deficient, right? But as we move towards right hand side, the objects are gas rich. You can see that they are also like more disc-like structures, and at the same time they also start appearing bluer, which means that like they are actually forming stars currently. This is where we have mostly old stars, not gas which can actually form stars as present, but here we have galaxies which are actually having gas which can form stars now, right? So if I point a telescope towards this radio telescope, I will be able to detect very little amount of neutral hydrogen in this, whereas like if I point towards this, I will detect large amount of neutral hydrogen in these. And same will happen also for the molecular gas. Molecular gas will also be in large amounts here, very small amounts here, right? So that story sort of that way connects. Any question up to this point? Actually, as of now, I don't understand this question, but maybe there is something deep in it. Let's come to it towards the end. So, what are the general properties of the ISM? The interstellar medium is generally confined to the disk or the halo, large range in temperature, right? That's what we talked about. It goes from 10 to Kelvin to 10 to the 6 Kelvin. So, gas can be really cool molecular phase to very ionized 10 to the 6 Kelvin. Right, which you will see in X-rays, for example. Large range in density also, 10 to the power minus 3 to 10 to the power 6 per centimeter cube. This is corresponding to the hot phase there, and this one is corresponding to the molecular phase here, 10 Kelvin, right? So, but nevertheless, these kind of densities we cannot even produce artificially in terrestrial our labs, right? So, that kind of densities we are talking about. So, it's a multi-phase medium. And it's also very clumpy and inhomogeneous, right? So we should not think of ISM as like something very uniformly distributed, right? Even if you recall the image of Orion Nebula that I showed, you saw a lot of structures in it at parsec scales, right? Filaments, clumps. So that's how everything is taking place, right? There are a lot of physical processes are happening. Places where like H2 region or a supernova is there are shocks formed, and the places where actually the gas is cooling, the clouds are collapsing, and the stars will form there, right? So there are a lot of structures happening at forming at parsec scales and even smaller scales. So what are the different phases of ISM? How do we classify it? I told you that like we have like molecular, neutral and ionized phase, but like even neutral clouds can have some ionized gas in between, or ions in them rather, right? Because that will depend on the ionization potential of what elements are present in that gas, right? 13.6 electron volt is the ionization potential of hydrogen. So there can be neutral hydrogen cloud, but it can have ions of carbon in it, because carbon has ionization potential which is lower than 13.6, right? So even if 13.6 electron volt photons are not present, low energy photons are there that can penetrate into the cloud and ionize carbon, right? So this means that like even a neutral cloud, when I say that okay, this is an H1 cloud, don't think of it as like it is like completely neutral. There may be small fraction of hydrogen atoms which may be ionized there, but even more importantly, there can be other elements present in it which can be in different ionization stages depending on what is the ambient radiation field present. So since hydrogen is the most abundant element in the universe, in ISM as well, we classify a cloud whether it's molecular, neutral or ionized based on what is the ionization state of hydrogen. So if hydrogen is completely neutral, we call it atomic cloud, then similarly ionized and molecular, right? So that's how we classify, but it's very important to remember that a neutral cloud can also have some ions in it, and they do play a very important role in actually determining the temperature of that cloud, for example. That's why it is important. So what is our goal? Our goal is to understand properties of these different phases, how are they maintained, and physical process involved. We will not really look at ionized and very hot phases in great detail, but we will focus mainly on the neutral phase, because that's more closely connected to our observations with S square kilometer array, and that also more closely connected with the issue of like whether galaxies have sufficient gas that can form stars or not, right? So that's the kind of question that we are trying to investigate today. But you can take this understanding with you and look at the textbooks and try to understand what may be happening in the ionized phase or the dense molecular phase. So neutral phase, atomic hydrogen, It's most abundant and simplest atom, right, that exists. Transitions, it has got transitions from ultraviolet to radio wavelengths, right. So we talk about Lyman alpha, then Balmer, Paschen, all these things, transitions are present or visible in like different bands. And then we have got 21 centimeter line, which we talked about yesterday, that is observable at radio wavelengths. It's and our interest, as I said, is because it's a key player in understanding how galaxies are forming stars. That's the focus. And this is just a schematic to tell you, like, there are these different transitions which we can see in ultraviolet, optical and infrared. So at this level, when we are talking about transitions between these n equals to 1, 2, 3, 4 levels, we are looking at what we call as 2n square degeneracy. But when we come to 21 centimeter line, we are talking about the hyperfine structure here, right. We talked about it yesterday, and it actually arises due to the interaction between the magnetic dipole moment of electron and proton. When spins are parallel and when spins are anti-parallel, these correspond to different ionization stages, and the energy separation there is corresponding to the 21 centimeter wavelength or 1420.405 megahertz in frequency, which is what gives it that name also. And you would remember from yesterday that this was first theoretically predicted in 44 and detected simultaneously by 3 groups almost simultaneously in 1951. So now what is it that we can learn from 21 centimeter line when we observe with a telescope? It may appear in emission, it may appear in absorption, and that we will try to understand in what circumstances that happen, but just at the atomic level what happens here, right? So we can understand this as a very simple 2-level system. You would have done in your basic physics courses like Einstein's A coefficient, B coefficient, those kind of a thing, and if at that time you wondered that why are we learning this, why are we spending so much time in this, so that time has come now actually to appreciate what was the purpose of it. So let us say these are the 2 levels of 21 centimeter line, these one, right, 2 hyperfine states represented here, 0, 1, and n1 and n2 represents density of atoms in these 2 states, and this is the separation. So this frequency is very well determined. So just from the Boltzmann law, we can actually estimate like what would be the n2 by n1, and if T is the temperature of the gas and these are the statistical weights of these 2, then we can write the level populations like this, right. This is a very simple thing which when we start thermodynamics, we write this equation without even thinking what it is, right. And if we substitute here Boltzmann and Planck's constant and value of this frequency nu, which is determined there, you will find that this h nu by k is just 0.068 Kelvin, right. You can calculate this, and this is a number you will find. So this becomes like 0.068 divided by T. T is the temperature, right. So when I was summarizing the kind of temperatures that we see in interstellar medium, what was that? That was going up from 10 Kelvin onwards, and 10 to the 6, right. And typically hydrogen gas actually will have temperature of few hundred Kelvin. So if I put 100 here and 0.068 here, and statistical weight of the excited state is actually 3, and this is 1, right. So this n2 by n1 is just approximately equal to 3, right, for any typical temperature in the neutral interstellar medium, right. So what isn't this appears like a magic actually, that without doing anything here, you find that most of the atoms actually are in the excited state. This does not happen at all, right, in general. You would not have imagined that ki like why you are not doing anything and then most of the atoms are in excited state. How does that happen? So there are various reasons for it, and let's look at some of them. So Einstein's A coefficient of 21 centimeter transition is actually this 2.9 into 10 to minus 15 per second. It's very small, right. As a result of this, the lifetime of state, which is just the reciprocal of this, 1 by this if you do, you will find that turns out to be 10 to the 7 here. So if I take an atom which is in F is equals to 1 state and leave it, it can take it this long to come to the ground state, right. So a problem for you is find out what is Einstein's A coefficient for Lyman alpha transition and estimate what is the lifetime of an excited Lyman alpha state like 2p to 1s transition, right. and compare it with this, that what is it that you get for n2 by n1 and what is it that you get for the lifetime of the state. But let's keep our focus here on 21 centimeter. So it has very low probability of transitioning spontaneously from excited state to ground state, right? So what can happen then is that now this gas cloud is at a certain temperature, and because of that there are thermal motions, right? And there will be collisions between them. So what is the collision cross section? We can calculate this if we know density, typically few centimeter cube in neutral ISM, we know from observations, and sigma, we just take it as the cross section of the hydrogen atom, and you calculate this, then your n sigma turns out to be that value, and you can then calculate what is the mean free path of collisions, right? Again, very simple thermodynamics we are continuing. If you estimate mean free path of collision, that is 10 to 15 centimeter, and again, like if from the Maxwell-Boltzmann distribution you can estimate the velocity, right? And velocity, you know everything, temperature, mass, this is Boltzmann constant, and now since you know both L and V, you can estimate what will be the time between collisions, and that turns out to be 200 years, right? So compare this 200 years with 10 to the 7 year, right? So this means that well before an atom can actually spontaneously transition from excited state to ground state, it will actually come down by collision, right? So collisions play a very important role in determining the level populations. What is level population? Level population is the ratio n2 by n1, right? That how many atoms are in excited state and how many atoms are in ground state. That's what, and we know it by a certain, give it a certain name, that is called spin temperature, to make it special for 21 centimeter line. But in atomic physics, this is nothing but it's called as excitation temperature. You would have come across this term, excitation temperature, right? In atomic physics, which determines the level population of it. So in case of 21 centimeter line, we just give it a special name called spin temperature. Now this spin temperature, why we give it a special name and not just leave it as temperature? Because these are level populations, right? These, this T here actually is the spin temperature. It may or may not be same as the thermal temperature of the cloud, right? That happens when only when there is a, it's in the thermodynamic equilibrium, right? And for, but in this case, if collisions dominate, then spin temperature can actually become close to the thermodynamic temperature. So this means that if I can somehow measure spin temperature of the cloud, I can also measure its temperature, right? Thermal temperature. So this is how we can relate the two quantities physically. But if it is not, then it means something else. That it will tell me that what are the other kind of conditions that are prevailing around this cloud. So this is how we can do some very simple back of the envelope calculations for interstellar medium, and then try to infer what kind of physical conditions this cloud may be in. So in observational astronomy, if you have to understand just one equation, this is that equation, I would say, right? Because when we are doing astronomy, it's like we are looking up and we are receiving photons, right? That's all. There is nothing else that we can do about it. You can put your telescope in space, but that will also do the same thing, right? We cannot go and touch, bring samples from the objects that we want to study. So radiative transport is the only way we learn about astrophysical objects. So this equation is telling that this is the specific intensity and this is the path length, right? So let's say if I am looking at this light which is coming from the projector, right, and it has a certain path length S up to me, I am talking about like how this intensity is changing per unit path length, right, as it is coming to me. So there are two things can happen on the way, right? One is that there is something else along the way that is emitting. So let us say there is a cloud in between here and it starts emitting, right? So it will add certain radiation to it at that particular path length value. Another thing that can happen, that there is another cloud or the same cloud, instead of emitting it is actually absorbing, right? So this is absorption coefficient and this is the specific intensity, right? So if it is absorbing, then this is why this minus sign is there, it will subtract, right? So this term will lead to, for example, an emission feature, and this term will lead to an absorption feature. They may or may not be at the same frequency, right? Because the clouds may be at different, the atoms or different species may be contributing to it. So at the end, this is what I will see, right? So we can do some solve the differential equation. It's very simple, like it's a like a 11-12 standard kind of an algebra involved here, and you can look at it in any astronomy, observational astronomy textbook, and you will be able to do this. And this is what you would get. I will just give you the solution of it. So this is the term which is actually corresponding to the absorption, like this gets absorbed, and this is the part which is getting added as emission, right? If there is no source behind, then there will be no absorption. I will see only an emission feature. If there is a bright source behind, then I will see it in absorption. That's roughly, you can try to understand this equation, but there is a lot more to it, which you should try to work out this algebra simple thing in the evening sometime, and try to understand that what each term in this case means here. We can also write this in terms of temperature, like brightness temperature, how we can take Planck's formula, take its Rayleigh-Jeans limit that relates specific intensity with temperatures. The whole thing gets can be rewritten in terms of temperature. This is the temperature of the cloud that I am talking about, right? And this is the temperature now of the, let's say, an AGN, which is at the background I am talking about, right? Or this bulb in this case. And this is what I am observing, and this tau is called the optical depth, which is represents the strength of absorption. So this is what I am observing, and this is absorption term, this is emission term, and if from both sides if I subtract this quantity, I can rewrite it like this, right? Very simple thing that I have done. So this is what I am observing, right? This is the differential I am observing here, and now you can see from this is that this will be positive if cloud temperature is higher, right, than this, the background source. This means that I will see it in emission, whereas like if it is less, then I will see it in absorption, right? So same cloud actually can produce emission or absorption depending on what is its relative temperature compared to the background source in this case, right? So same cloud, depending on what is its temperature, can appear in emission or absorption, and if it turns out to be same, then this term will become 0, and in that case you won't even know that it exists, right? So this is how I can look at as something in the sky and determine its properties. Continuing further on this, if you go back to your Einstein's A and B coefficients, we can determine an absorption coefficient like this. This is Einstein's B coefficient, B12 and B21. What do they represent? If you recall, what are the transition probabilities for spontaneous and simulated emission and absorption, all those things, then you would find that this is how it can be written. I don't want, you will get these slides, right? So you will don't have to really worry about taking notes of it, but I can write this absorption coefficient simply like this in terms of B12 and B21, which is the Einstein's B coefficient, right? And if I substitute this in optical depth, actually I just get this, I will get this simple quantity, which is the density of hydrogen atoms in the cloud and the spin temperature that I was describing, right? Whereas like if you do the same thing for emission, in which case this equation is just this much, because as I was telling you, if there is no background thing, cloud there, then this is not there. So if you are talking about only emission, then I am having this term, and you again like do the approximation for small optical depth, then this becomes Ts tau nu, and it's just proportional to, and you substitute this, then it is proportional to the number of atoms present, right? So let's try to understand what this means, because algebra is like, in this case, not even high school algebra now, right? It's not even 12 standard. You can do it in 10-15 minutes after you get the slides, or you refer to any standard observational astronomy textbook. Is that in case of absorption, it is proportional to number of hydrogen atoms, but inversely proportional to spin temperature of the gas, which is the ratio of level populations, right? In case of emission, it is actually proportional to only number of atoms, right? So what does this mean actually in observationally? So this is what people saw when they did observations of different hydrogen clouds for the first time. What they did was that, let's say there is a hydrogen cloud, point telescope towards it, and you get this kind of an emission line, right? And then when just close to the cloud, if there was a very bright radio source, an AGN, you point a telescope such that it is passing through it is observing cloud as well as the background source. Now then in that case absorption will be produced, right? So this is the absorption spectrum which comes from the same cloud, right? So same cloud is detected now in emission, in absorption, and these are different examples of that. Isn't it obvious to us that absorption all the time is actually confined to much smaller velocity range compared to emission, right? You can see that in almost every case you have a broader component which is extending to much larger velocities. X-axis is velocity here. You can see that there is always a very broad component which is there in emission, but in absorption there is only one narrow component, right? So what this is telling, if you go back to this equation and try to understand that absorption is actually not only depending on number of atoms but also the spin temperature. So what happens that if gas is actually warmer, then optical depth will be smaller. This means that it will not be able to produce much absorption. Whereas like when the gas is cold, I will be able to actually produce much stronger absorption from that. So this means that there is this total gas which is present, which has warm component and cold component, and it is seen in emission. But when I am looking at the absorption signal only, then only cold component is contributing to absorption. That's what is happening, right? So this was the evidence. This was done in 60s and 70s, which told us that neutral hydrogen which is distributed in our galaxy, actually this is H1 emission map of our galaxy, right? It's actually in at least two phases. There is one phase which is called cold neutral medium and another phase which is called the warm neutral medium, right? And this is just showing the cycle between different phases. I will not go into this right now. Let us continue to keep focus on warm neutral medium and the cold neutral medium. So these are two different phases. It is still an active phase, a topic of research, that how much of the gas in our interstellar medium is in cold neutral medium and how much of it is in the warm neutral medium. This actually representation of a model, basically, this curve. I don't want to go into details of explaining it, but what is important to understand here is that in interstellar medium there are a wide range of physical processes that contribute to heating of the ISM, right? For example, if I turn on a star, it photonizes gas, electrons coming out with extra energy, that is contributing to heating, right? Where like on the other hand, if there are atoms which recombine, atom electron recombine and they emit a photon and that photon emits a cloud, that's loss of energy for that cloud, right? So that is equivalent to cooling. So in ISM there is a bunch of processes that are contributing to heating, another bunch of processes corresponding to cooling. So if I make a list of all those processes, balance them and try to determine like then what would be the distribution of gas in warm neutral medium and cold neutral medium, this is the kind of thing I will get, right? So knowing how much of gas is actually there in these different phases is really important to understand what is going on in the ISM. That's why this is still an open question, because people, observers want to get a more accurate measurement of this. Cold neutral medium generally is temperature of 100 to 200 Kelvin and warm neutral medium is generally temperature 500 to 8000 Kelvin. That's the kind of temperatures we are talking about. If you go to ionized phase, that is 10 to the 4 Kelvin, and then even very hot phase is 10 to the 6 Kelvin. So this is the kind of distribution of gas phases we have, but what we have done up to this point is that we have focused on that what is it that we can learn about ISM using the 21 centimeter line, right? So any questions up to this point? So you will have these slides, you will get a deeper understanding of these things if you go and work out radiative transport equation and you try to figure out like how the same cloud can actually be seen in emission and absorption depending on the relative difference of the temperature of the background cloud and temperature of the intervening cloud. And then another thing which at some point you will get confused by the time we finish this is that there are so many temperatures we are talking about. There is temperature of cloud, then there is stream temperature, there is brightness temperature. There is, to tell you in very simple terms, so we have one temperature which is thermodynamic temperature that we talk about. So if I just say temperature, it is that temperature, right? But when we talk about spin temperature, it is nothing but excitation temperature. That is a measure of the level population. It may or may not have anything to do with the thermodynamic temperature, right? That will depend on if the collisions are determining what are the level populations, then it will be in thermodynamic equilibrium, and in that case the excitation temperature, spin temperature will be thermodynamic temperature, otherwise not, right. Third temperature we introduce is the brightness temperature. Brightness temperature is again nothing to do with the thermodynamic temperature. It is just a we have used a Rayleigh-Jeans limit of Planck's equation and written a brightness in terms of the brightness temperature, right. That's all we have done there. Because if you use that and take an AGN and estimate its temperature, you will find the temperature turns out to be 10 to 12 Kelvin. Of course, it is not thermodynamic temperature, right. It is just a measure of its brightness. So these are three different temperatures which you will come across in literature. They are all three very different, right? Yes. Yes. Yeah, NH is also not same for both. Like you think of it like there is a total NH in a cloud, and the total NH you will see it in emission, regardless of what is the temperature, right? And but now when I talk about temperature, then this NH is actually in two components. Let's say one fraction of NH is like at a low temperature, and another fraction of NH is at high temperature, right? So the low temperature NH is what is producing absorption. High NH temperature is not producing absorption. So that's why we start seeing difference in the two profiles. So now once we get a little idea of like what kind of stuff is going on in the interstellar medium, right? So this gas will come to warm neutral medium, cold neutral medium. This is how it is distributed, neutral hydrogen. What is it that we see at the galaxy level? That's what we are interested in now, right? So this is how a typical disk galaxy may look like at different bands. So this is the atomic gas. This is 21 centimeter line map, right? And this is what you see is the star formation rate measured using optical or ultraviolet, right? So you can see the star formation is happening at a much smaller level compared to the region over which H1 is present, right? And this we generally see for disk galaxies is that H1 disk, size of H1 disk is typically factor of 2 compared to the stellar disk, right? So there is this disk which is large, the star formation is taking place only within half of it in diameter, right? And you can see that molecular gas is also in this part, right? So this is a clear demonstration of that stars are actually forming from the molecular phase, right? But of course this gas in the outer regions needs to continuously flow because this is getting used to form stars, right? So that supply of gas has to be maintained. So outer disk does play a role in sustaining this star formation, but eventually it's the molecular gas which is determining where the stars are forming. And if we want to know where the stars are forming, then we need to look at it in near ultraviolet generally, because at longer wavelengths what we will see is actually obscure star formation or older stars, right? So this is now happening at the galaxy level, right? So galaxy level, what happens that galaxy is formed with a certain amount of gas, neutral gas in it. It starts forming stars, and that gas is now getting continuously used to form stars, right? And at some point stars will start dying, and that gas is now getting ionized and maybe even getting expelled from the disk of the galaxy, and there will come a time that it is forming so much stars that it does not have enough gas to form stars, right? At that point it can actually transition to a state where it stops forming stars. That's where we can call that it becomes what is called red and dead a galaxy. And but if we somehow it manages to accrete more gas from the intergalactic medium and it can continue to form stars, then it can continue its journey. And how do we understand this? We understand this by something called the main sequence of galaxies. This is at redshift equals to 0. X-axis is stellar mass and y-axis is star formation rate. Both are plotted on in log scale, And you see that like if we focus only on this part, there is actually a linear relation between star formation rate and stellar mass, that as the mass is increasing, star formation rate is also increasing. This corresponds to the main sequence of this. If there is a deviation from this, those galaxies are called starburst. They are forming much more stars because of conditions and supply of gas. They are starburst galaxies, but when the supply of gas is not there, then they start deviating, and this is the part which we refer to as these kind of galaxies, where the star formation has stopped because no more gas is available from which stars can be formed, right? So this is how a galaxy journey can happen. So we can, by observations of stellar mass and star formation rate of a galaxy, can learn a lot about it. So this main sequence is known to exist up from redshift 0 to up to redshift of 6, and maybe now people are observing galaxies at higher redshift, so even there this will be maybe observed. But what we see that like this main sequence is present. What is different as we go to different redshifts is the normalization, right? As we go to higher redshifts, galaxies are forming stars much more vigorously. That's what is observed generally, right? Another thing that we can learn, let's say if they are galaxies, I observe them. There is another very nice relation that we can observe, that is called baryonic Telly-Fisher relation. Again, like it's a very fancy name, but what this is a very simple plot. X-axis, this is the original plot. X-axis is the velocity, the vector velocity. So x-axis is representing how the galaxy is spinning, and y-axis in this case is magnitude, absolute magnitude of the galaxy. So its brightness, its total stellar content. You can it's a proxy for that, and there is a very nice relation between them, right? So brighter galaxies are actually rotating faster. That's the very simple conclusion that you can draw, right? And then subsequently it has been converted into something which is more robust. Y-axis here is the baryonic mass, that is the total matter that is in the galaxy, and then x-axis is again the velocity of it, and you can find that again like over such a large scale there is a very nice relation in this case. And so you can now see, right, like what we have done over last few slides. We looked at gas physics at cloud level in the interstellar medium. Then we looked at like how the total gas content and star formation may be related, and now we are talking about like how this may be related to the overall kinematics of the galaxy and its immediate environment, which is called as circumgalactic medium. Again, there is a very nice relation exists between the H1 diameter of the galaxy and its size. You can see that like it's a beautiful nice relation that exists, and in addition to it there are a few more relationships exist between the H1 content of galaxy. So this is y-axis here is total H1 mass divided by stellar mass, so mH1 by m star we call it, and x-axis in this case is stellar mass. In the last one it is near UV minus R magnitude. It's as we were looking at those images of that particular galaxy, we saw that like if we look at it in near UV, that's is more sensitive to picking up the recent star formation that is going on in the galaxy, right? So availability of gas is related to stellar mass to ongoing star formation. So these are the very simple scaling relations that we can determine by observing a bunch of galaxies in this H1 mass and their properties at different wavelengths, right? And using these we can then actually start asking bigger questions about galaxy evolution, that how galaxies like let's say even in our local universe are forming stars, in which environments the star formation is more or less, what type of galaxies form stars more efficiently. Once we have a decent understanding of those questions at redshift equal to 0, then we can start asking questions that how these things are now changing if I go to let's say slightly higher redshift, 0.05, 0.1, or when universe was let's say 50% of its age, and so on. So that's what this is all these questions come under this broad topic of what we call as galaxy evolution, right? So what this involves typically is that like we standardize and understand all these different relations that we have looked at redshift 0 in variety of environments. These environments could be like we look at isolated galaxies, we may look at galaxies which are actually in groups, we may look at galaxies in clusters, so that we also understand that how galaxy properties are changing as we go from one environment to another. Once you put all these together, then we can start asking questions that how any of these are actually evolving as a function of redshift, right? So how will SK help in all these things? And the simple answer to this is that 21 centimeter line is very, very weak, and until like say a few years ago, we only could detect H1 emission from galaxies at redshifts of like let's say 0.2, right? And that too by integrating in small regions of sky for 100, 200 hours, right? That's all that was possible, and it's only now with Meerkat that there are now a bunch of detections that are possible at redshift of 0.3 and 0.4. So if we really want to ask these big questions for galaxy evolution over the lifetime of the universe, then we need to be able to detect H1 emission to very high redshifts very easily in a routine manner, right? And that's where SKA will help, and that's one of the key goals of a square kilometer array, that is to be able to detect H1 emission directly from galaxy at redshift of 2, right? And why redshift of 2 is interesting, I'll talk about that. But to organize community's effort towards building a square kilometer array and to actually be able to answer all these questions, yesterday Abhirup talked about that we have different working groups. So for a square kilometer array, we have a working group at international global level, that's SK H1 Science Working Group, that's chaired by Betsy Adams from Netherlands, me, and we have a corresponding working group in India that is chaired by Narendra, who is sitting here. So there is through these we are organizing effort and trying to organize that big question that we answer using SK in the field of galaxy evolution. So what are the topics that we are looking at? We are looking at, of course, H1 neutral hydrogen, that's the main tracer we have, and I have shown you that how it is important interface between molecular gas which is forming star and then the gas that needs to be continuously accreted from the ambient medium so that galaxy can continue to form stars. If that does not happen it will form star. So with SK we want to observe that gas in our galaxy in emission and absorption. Why in emission and absorption? Because if I can do both, I can know the physical state of the gas. You know that like these two different temperature phases exist, and if I can do both emission and absorption, I can actually understand what is going on. Then we want to also go outside our galaxy, right? And there we want to look at not only absorption from normal galaxies, but we also want to be able to look at absorption from galaxies which have got AGN that Dharam was talking about. Why is that? Because that will allow us to understand that two questions. First question is that how this AGN, when it turns on, changes the property of cold gas in the galaxy, and if it changes it, then it will affect its ability to form stars, right? So that is AGN feedback at the galaxy level itself, how that is playing role. And then when a galaxy in a galaxy supermassive black hole has to become active, it has to accrete matter, right? And that accreting matter has a molecular phase and cold atomic gas as an important component. So through these observations we can also understand that how this matter actually comes so close to the supermassive black hole and can actually become like a part of matter which is actually feeding this black hole and becoming active. And then we want to look at these galaxies in emission, nearby galaxies, distant galaxies, to look at evolution of H1, and also look at galaxies in different environment, right? Because that's environment plays a very important role in how galaxies evolve. So for this, what SK will do, SK will actually look at different regions of the sky, favorite objects of different astronomers. But to answer some of the big questions, we will need actually very large surveys, very deep surveys, so that we can detect very faint objects up to redshifts of 1 and 2, and we can also detect very faint galaxies even in the nearby universe. So these are the different kind of surveys that were proposed in 2015, that community identified, not proposed, because call for proposal has yet to happen. And now in 2025-26 we are revising those because telescope's capabilities are going to be much more realistically and better determined in next few years. So we will now know what exactly can be done with square kilometer array. So these will be revised. So but you can see that people are planning to look at do surveys which are like several thousand hours, right? So that's the kind of integration over the sky that will take. And why that is important, because this will lead to data volumes of petabytes in size, right? Several petabytes of data sets will be produced, and these then need to be processed, and then images need to be formed from that. So it will be a very big effort in terms of like organizing data analysis, computing, and all that stuff. So it's not something which can be done very routinely. So all the hardware, software needs to be organized in advance, and this is something which we have not done before. Like when I was a PhD student, I was collecting data from GMRT. My 8-hour observing run will be like 2 gigabytes, right? Today I am collecting data from Meerkat. My 1-hour observing run contains 1 terabyte, right? And square kilometer array will produce 2 petabytes in a day, right? So we need to devise new methods at every stage to be able to actually understand that what is, to be able to do these things that we are talking about. So next few slides I will just tell you that what we are doing at IUCAA in particular. So we are using Meerkat telescope to carry out this large project called Meerkat Absorption Line Survey, in which we are carrying out a large survey involving 400 pointings, total observing time of 1500 hours to look at H1 gas in absorption at redshift 0 to 2. And in next slide I will show you that why, and in terms of observations we have completed 1300 hours. So we have close to 1.5 petabytes of data at IUCAA, which we have nearly processed. And these are the specific features of Meerkat telescope. It has got 64 dishes. Now there is a Meerkat Plus which exists, another 16 dishes, and it has, for Meerkat absorption line survey we are using these two bands, L band and UHF band, that's called MALS, and we are taking data over this entire frequency range, which corresponds to redshift 0 to 2. And why this is important, redshift 0 to 2 is so much of interest for different instruments and different projects, because if you look at how galaxies are forming stars as a whole as a function of redshift, and this is something which can be observed using various emission lines at optical, ultraviolet and infrared, then this is what we will see actually, right? And x-axis is redshift and y-axis is what we call as the star formation rate density. So this is star formation. You can see that as we go from redshift 0 to 2, it increases by almost an order of magnitude, right? And then this is peaks here. This period is called as cosmic noon. That's where the star formation rate density is peaking, and then it starts falling, right? So these are completely observational thing. Now the question that is astronomers are asking, that what are the processes that are driving this evolution, such rapid evolution over this? So a very practical and simplistic at the same time way would be to ask that, okay, let's measure how the molecular gas content of galaxies is evolving over the same redshift range, and also how the atomic gas content of galaxies is evolving as a function of redshift range. And these are some of the measurements that exist. You can see that these are molecular gas measurements. They are much better. The atomic gas measurements are actually quite noisy still, right? Some measurements are coming from stacking experiments, but still a lot of work needs to happen when we are looking at to understand the evolution of atomic gas, right? Because the idea is that when we have these two measurements, then we can say that at what rate these galaxies are actually acquiring atomic gas from the ambient medium, and then how it is going into forming stars. And once we can put those terms in the equation, we will have a reasonable understanding of what is actually leading to this evolution. So this is one of the big questions that actually we are taking some of the first steps towards this answering with MALS, and then at the same time much more work will be done with the square kilometer array in this direction. So recently for MALS we have done 3 data releases. One in the first phase, using L band, we released a catalog of million radio sources. So these are images which have sensitivity of 10 to 20 macrojansky at a resolution of 8 to 12 arc second. So what this figure is showing here, starting from 1940 to 2025, various radio surveys, and these are the number of radio sources that have been detected in various radio surveys. So this is starting from like first, this is Gotha River here, first measurement, and now we are talking about surveys which are detecting several million radio sources. This is where MALS is sitting, and when we combine UHF band here, we will be actually comparable to some of the largest surveys that are doing this. And recently we released another million source catalog and also a measurement of cosmic dipole. You will learn about cosmic dipole and these kind of topics in cosmology science case. I am sure Pankaj will talk about it. Then we recently detected some 3,500 absorption signals from our own galaxy. So this is something which is now available. So our objective is that all the data that we are taking and all the data products that we are producing out of MALS, including calibrated visibilities as well, these will be made public, all of it over next 2 or 3 years. And these are some of the various results that we have gotten, like some high redshift absorption, detection of recombination lines. This is absorption associated with the AGN itself. In this case, this is the H1 emission showing that these two dwarf galaxies are interacting with each other. And this I have already talked about is corresponding to absorption from our own Milky Way galaxy. And this is a detection of absorption associated with an AGN at redshift of 1.4. So this is so when we have a very sensitive and wideband instrument, this is a wide range of science that we can do. And so when we are preparing to actually work with square kilometer array, this is the kind of sophistication we have to bring to the data analysis. And also, like there is a wide range of science that can be addressed, and that also we have to sort of tune ourselves to doing. So if you want to know more about this project, you can look at the website. And as I said, the important thing is that all the data products are being released, so you can actually go ahead and start planning your projects with them as well. And if there is something that does not exist, you can reach out to any of us. And if you are thinking more futuristic and want to get involved in like how SK Science is getting planned, especially for H1, you can talk to Naren. He is chairing the working group here in India, and you can reach out to any of the other working group chairs, like for international one, it's Betsy and me. And you can find out these details at Mars website, at SK India's website, and also Square Kilometer Array Office's website. So all this information is publicly and very easily available to you. Spend some time in looking at all these details and talking to any of us now as well as afterwards. Okay, thank you.